This is section 1.5a, graphs of functions. First, let's look at an illustration of a function. And I know this is probably going to seem very basic to you because you've seen stuff like this in Algebra 1 and 2. But again, as I said before, since functions are so important for calculus and for the rest of this course, it does help to make sure that we're crystal clear about functions. All right, so this is a function. It doesn't matter what it is specifically, but we see that it's a curve, y equals f of x. And what that means is that for every point, for example, this point here that I'm circling now, this point has an x-coordinate of x and a y-coordinate of f of x. F of x is the value that you get for the function when you plug in x. Now, the next thing we're going to talk about is the vertical line test. And the vertical line test is a graphical way to test whether a curve is a function or not. Recall from the last section that a function is defined as a relation in which the elements of one set are mapped to or connected to exactly one member of another set. Okay, that exactly one part of the definition is important because if an element in the domain is matched to more than one element in a range, then it's not a function, okay, by definition. A function is such that for each element in the domain, there is only one element in the range. One element in the range that goes with it. All right, and we can see that graphically with the vertical line test. All the vertical line test means is that if you have a curve and you draw a vertical line, any vertical line through it, you can pick where you put the vertical line. If you draw a vertical line through it, then it must cross the graph in only one place. It cannot cross the graph in more than one place. If it does so, it's not a function. All right, so all of the graphs on this page, on this particular screen, these are functions because they all pass the vertical line test. Okay, so let's look at this this first function here in the upper left. This is a sine wave, y equals sine x. And if you follow where my arrow is, where the cursor arrow is, you know, I can trace the vertical line anywhere I want. Let's say I trace the vertical line right here at negative 3 pi over 2. And I'm just making a vertical line there up and down. Well, that vertical line crosses the graph in only one point. And therefore, this is a function because the definition of a function is that for each element in the domain, there is only one element in the range that's matched with it. Okay, so the sine curve passes the vertical line test. This next curve in the upper right, this is what a cubic function looks like. A cubic function, when you have a polynomial in which the highest degree of x is 3, cubic function. Well, this cubic function shows that it passes the vertical line test because if I do a vertical line through the point 3, for example, like I'm doing right now, that vertical line crosses the graph in only one point. How about here on the lower left? This is a parabola, a vertical parabola, also called a quadratic function. And it again passes the vertical line test, which you can clearly see. And finally, in the lower right, we have a simple line. Horizontal lines, diagonal lines, every line passes the vertical line test, except, of course, a vertical line. And a vertical line is not a function, but every other line imaginable besides a vertical line is a function because it passes the vertical line test. The vertical line test is simply a graphical way of expressing the definition of a function, which is that for each member of the domain, there is only one element in the range that is matched with it. Now, keep in mind, lest you become confused, that it is possible for elements in a range to be repeated. Now let me give an example of that. Look at this lower left function, this parabola. Okay, right now I'm circling with the cursor arrow, I'm circling the number 1. Okay, so let's say at that point the x value is 1, and it has a specific f of x, which looks like about 1/2. Okay, now notice though that if I go on to this other point, -1, where x equals -1, well, it also has a y-coordinate of 1/2, okay, because this graph is symmetric. Now, it still does satisfy the definition of a function, because all the function means is that for each element in the domain, there is a unique element in the range that is mapped to it. However, that does not necessarily mean that elements in the range won't be repeated. And we see an example here because the element in the range 1/2, which is mapped to the x-coordinate 1, is also mapped to the x-coordinate -1. However, for each x-coordinate, there is only one unique y-coordinate. Okay, now later on we're going to get to a specific kind of function called one-to-one, where the function also passes a horizontal line test. But for now, we're just looking at the vertical line test, which tells us whether something is a function or not. Continuing the vertical line test, here are some examples of graphs that do not pass the test. Here in the upper left, we see how we have this crazy looking curve, and it clearly fails the vertical line test in several places. Therefore, it's not a function because it violates the definition of a function. Let's look at this x-coordinate 1, for example, that I'm circling right now. Well, for the x-coordinate 1, there are 3 different elements in the range that are mapped to it, and that, of course, violates the definition of a function, which says there can only be one element in the range mapped to each element in the domain. This next example here that I'm circling now, this green curve, is an ellipse. You saw those in chapter 10. Well, ellipses are not functions. Ellipses are not functions. They are relations, but they are not functions. They do not pass the vertical line test. And finally, sideways facing parabolas, which you also saw in chapter 10. Those are not functions. They are relations, but they are not functions, because for each element in the domain, there can be more than one element in the range that is mapped to it. Now let's talk about finding zeros. You've done this before. The key thing to review here is what a zero is, because sometimes we hear the word zero and we get confused. A zero is simply an x-intercept. Okay, we're very familiar with what y-intercepts are. Well, that's where a curve or a line crosses the y-axis. Well, an x-intercept is simply where a curve or line crosses the x-axis. And an x-intercept is a synonym for a zero. And this graph illustrates that. Here we have a simple quadratic function, a vertical parabola, and the function is x squared plus x minus 6. This is what its graph looks like. And it has a vertex, and it also has two x-intercepts. And these x-intercepts we call zeros. All right, so the point of this screen here is just to review what a zero is and to see what that looks like on a graph. Another example, we can find zeros graphically if we have an accurate graph, as we do in this case. This is the function f of x equals negative 0.3 x cubed minus 0.3 x squared plus 0.6 x. And you can graph this on your calculator, but this is what you'll get. These are the zeros. Okay, negative 2, which I'm circling now, is a 0. Another 0 is the point 0 at the origin, and another 0 is 1. Okay, x-intercepts. Now, x-intercepts and zeros are often given with both coordinates. For example, I could call this point, which I'm circling right now, I could call this point the point 1, 0, and I could call this point the point 0, 0, and I could call this point the point negative 2, 0. And that's perfectly accurate. But many times, zeros are mentioned simply by the x-coordinate, since the y-coordinate is assumed to be 0. In fact, that's where we get the name 0, because the y-coordinate is 0. And so the x-intercepts are where the y-coordinate of a graph is 0. In other words, where it crosses the x-axis. Now let's review finding zeros algebraically. This is something that you did in Algebra 2. We're going to be doing it a lot, especially in the next chapter, in Chapter 2. But it's important to review this now. Obviously, you can find zeros graphically just by looking at the graph and seeing where the x-intercepts are. But how do you do it algebraically? Well, let's look at this first example. Find the zeros of f of x equals 3x squared plus x minus 10. Now, we know that we want to find the x-intercepts. And we know that x-intercepts happen when the y-coordinate is 0. And so, this is something you probably already figured out, you simply plug 0 in for f of x. So you set 3x squared plus x minus 10 equal to 0 and solve for x. Okay, so pause the video, do that, and then resume when you have your answers. You should have gotten these two answers, 5/3 and negative 2. 5/3 and negative 2 are the two zeros for the function f of x equals 3x squared plus x minus 10. Find the zeros of g of x equals root 10 minus x squared. Okay, so follow the same procedure. Set the function equal to 0 and solve. Pause the video and then resume when you have your answers. You should have gotten root 10 and negative root 10, plus or minus root 10. Root 10 and negative root 10 are the zeros for the function g of x equals root 10 minus x squared. Find the zeros of f of t equals 2t minus 3 divided by t plus 5. Okay, pause the video, get that 0 or zeros, and then resume when you have an answer. 3/2. 3/2 is your answer, because 3/2 is the only thing that you can put in for t in order to get a value of 0 for f of t. Finally, find the zeros of f of x equals x cubed minus 4x squared minus 9x plus 36. All right, so at first sight, this looks pretty daunting because we have a cubed in there and we're not used to seeing that. But this is possible, and it's possible by grouping terms. All right, so try to group the terms in a way where you see a pattern. And if you get stuck, I'll walk you through how to group the terms, and then you'll clearly see how to proceed from there. So pause the video, figure out how to group this if you can. If you get stuck, don't worry, just resume for the factoring. All right, so you should have started by grouping terms like this. You take the x squared out of the first two, and you get x squared times x minus 4. Then you take the negative 9 out of the next two. You get negative 9 times x minus 4. And now you can see the pattern, right? You can see the pattern because x minus 4 is repeated. And that's just like distribution. So we can rewrite this as x squared minus 9 times x minus 4. And this is the factoring of x cubed minus 4x squared minus 9x plus 36, which we did by grouping. Okay, now if you haven't already gotten your zeros for this function, you should be able to get them now. So pause the video, get the zeros, and then resume when you have them. So the zeros for this function, f of x equals x cubed minus 4x squared minus 9x plus 36, are 3, negative 3, and 4. Each of these values, 3, negative 3, 4, if you plug them in for x, will give you an f of x value of 0. Now, the last thing we'll talk about today is the terms increasing, decreasing, and constant. And these terms simply describe how functions behave. All right, so increasing means the value of f of x is going up. Decreasing means the value of f of x is going down. And constant means the value of f of x is staying the same. All right, so do you see how for this left portion of the parabola, if you follow where my arrow cursor is moving, well, for that left portion of the parabola, I can see that as x increases, as x moves from left to right, well, the value of f of x, or the y-coordinate, the value of f of x decreases, it goes down. Then it reaches its minimum here at the vertex, and then the whole right portion of the parabola, as the value of x increases and goes from left to right, well, the value of f of x increases also, and so this would be considered an increasing interval. All right, the function is increasing along this interval. Now, how do we write this? We write it this way. We would say that this function, this quadratic function, is decreasing on the interval from negative infinity to negative 0.5. Notice that the intervals are talking about x-coordinates. Okay, so from the x-coordinates negative infinity to negative 0.5, what is happening to f of x? Well, f of x is decreasing on that interval. It's going down. All right, but the function is increasing on the interval from negative 0.5 to infinity. That is the x-coordinates negative 0.5 to infinity, because for those x-coordinates, what's happening to f of x? It's increasing. It's going up. Okay, so this is just a brief introduction to the terms increasing, decreasing, and constant. We're going to see a couple more examples now. Let's look at this function. This is called a piecewise function. A piecewise function just means that the function is defined in different ways for different intervals. So like for this example, you don't have to know the specifics, but this would be a horizontal line for this interval, then it would be a diagonal line for the next interval, then it would be like half of a parabola for the next interval, and then a horizontal line for the final interval. But in any case, this is just to illustrate the terms increasing, decreasing, and constant. All right, now let's see if you can do this on your own. All you have to do is put it into words and say on what intervals this function is constant, on what intervals it's decreasing, and on what intervals it's increasing. Okay, so pause the video, try and do that on your own, and then resume when you have an answer. You should have come up with this. This function is constant on the interval negative infinity to negative 4. It's decreasing on the interval negative 4 to negative 3. It's increasing on the interval negative 3 to 0. And it's constant on the interval 0 to positive infinity. One last example of increasing, decreasing, and constant. All right, so you should be able to do this on your own. Pause the video, write out the intervals for the increasing and decreasing, and then resume when you have an answer. And this should have been your answer. Decreasing on interval from negative infinity to 0, increasing on interval from 0 to 2, and finally decreasing on the interval from 2 to infinity. Here's the classwork, page 61. Please write these numbers down, and we'll see you in class.